let's begin then the last lesson of chapter 5. It's a shorter lesson, or shorter chapter, 4 lessons on inequality. If you remember the previous lessons, we had some properties that introduced inequality, like whole greater than part. We had the fact that an exterior angle is greater than either remote interior angle. In the last assignment, we had that if two sides of a triangle are not equal, the angles opposite them are unequal in the same order, and the converse idea of that. Today we have the triangle inequality theorem. Kind of an intuitive one, and in class we will probably go at this with spaghetti. So, not wanting to spoil that activity, we'll just show these pictures up here, and maybe they'll give it away a little bit. Maybe not. 6793, how long is that one? So maybe looking at that, you can kind of get an idea where we're going with this theorem. We're adding those two together and saying it has to be greater than this, VE. Adding 67 and VE, saying it has to be greater than 93. Adding 93 to VE, it's got to be greater than 67, which kind of gives us an idea where VE would have to be. So here is the theorem. The sum of the lengths of any two sides of a triangle is greater than the length of the third side. Your book has quite an involved proof on this. It's a good proof though. Here's a triangle. We're saying that this blue one plus this red one has to be greater than the green one. What they're doing is they're adding some stuff to this, and you can see they added BD and made it the same as BC. Kind of gives you a hint then. We've got two sides of a triangle equal, making those two angles equal. If you draw a line in here, it looks like we've got a ray between two other rays. So we've got two angles down in here. Notice those two are the same length. Creates three different angles that we'll use in the proof here. So here it is. The sum of any two sides of a triangle is greater than the third side. We're trying to show that AB plus BC has to be greater than AC. Realistically, you'd have to prove that combinations of the other sides would be greater than the remaining side as well, but here's a proof on this one. Try to come up with the reasons for this before I show you. ABC is a triangle, certainly given. Why can we draw line AB and just run it way out here into nowheresville? Correct, because 2 points determine a line. Now we're going to choose point D out here so that BD and BC are the same length. What allows us to create a segment of a certain length? Correct, the ruler postulate. We're going to draw CD. Of course, 2 points determine a line. So we've got a triangle there. Triangle in which we have two sides equal. So we can say angles 1 and 2. Notice down here is where we ended up with those two guys. Saying 1 and 2 are equal. If two sides of a triangle are equal, the angles opposite them are equal. Now we're back to the betweenness of rays. ACD is equal to angles 2 plus 3, betweenness of rays theorem. And now, why would ACD be greater than angle 2? Newly learned property, the whole greater than part theorem, I guess it is. ACD greater than 1. ACD greater than 1. So we've got this angle down here greater than 1. Yes, we're looking at 5 and 7 substituting. We have AD greater than AC. AD greater than AC. Well, we just said that those two angles are not equal. So if two angles of a triangle are unequal, the sides opposite them are unequal in the same order. So now we have AD greater than AC. Now out of the clear blue, AB plus BD is AD. Well, we used betweenness of rays up here. Now we're going to use the betweenness of points theorem. into that theorem, notice the left sides are not that different, we are going to substitute the fact that AD is greater than AC. So we're going to take AB plus BD and substitute it in for the AD right here. Since these two are equal, we can substitute either one. So we have AB plus BD greater than AC. We're really close. BD and BC are equal. So now we can say AB plus BC is greater than AC. Substitution steps 3 and 11. So we've proven the only theorem today that the sum of the lengths of any two sides of a triangle has to be greater than the third. And people made fun of Euclid when he put that in his book, The Elements. So obvious even a donkey wouldn't need proof. If a donkey were here and the food was there, he wouldn't walk from D to P and then P to H. He'd walk from D to H. It's obvious. Couple questions on that. State the theorem. Trying to get you to memorize it, trying to help you memorize it a bit. Write the inequality from here that the donkey would know. Well, if he's only going to walk here, what does he know about that compared to these two? So write the inequality and then write the other two inequalities, practicing it. And then some questions to talk about the difference between a theorem and a postulate. 3 celestial bodies, Earth, Sun, Venus. Venus and the Earth revolving around the Sun. Sometimes they're a triangle, and sometimes they're not. Sometimes they're lined up perfectly. So a couple of questions about this. What relation exists between the three if they don't determine a triangle? And then they give the distance averages between the Sun and the Earth is 93. No matter where the Earth goes, it's about 93 million miles from the Sun. No matter where Venus goes, it's about 67 million miles from the Sun, anywhere along that circle. So now they have a few questions here. Tell whether each is possible, and then find the distance between the Earth and Venus. So you're working through those, a couple of pictures that may help you. Once again, we're back to the spotter problem. Remember, the spotter wanted to get to the corners A, B, and C because he was trying to spot a ship so they could get off this equilaterally shaped island, which was 12 kilometers on the side. He built a hut in here. We're going to use what we learned today about the triangle inequality theorem. Copy and complete. Copy and complete. Replace each question mark with a number, so we're looking for a value in there. I can help you with the first one. PA plus PB has to be greater than the third side, which is 12. So put a 12 in there. Continue with that idea. Now if you look here, the inequality, the greater than sign is way over here. What's on the left? Where did that come from? What would be on the right? Which number? Look at number 10. How is 12 compared to number 11? Here we had PA and PA. Now we got 2PA. What number belongs here? What's different between 12 and 13? And again, we need a number here. As long as the spotter builds his shelter at some point within the island, what can you conclude about the sum of the lengths of the paths from his shelter to the corners? Here are the paths, PA, PB, PC, and here they are, PA plus PB plus PC. So what can you conclude about the sum of those lengths? We have a couple of problems here that are pretty good challenges that test whether you actually understand the triangle inequality theorem. So x is an integer between 2 and 7. Remember, an integer is, it's got to be a number without any fractional or decimal part. How many different triangles could you make that were 2, 7, and x? Remember what x has to be. kind of helps you out here. Could x be 3? Explain why or why not. What is the answer to the problem? How many different triangles are there? Continuing. Very first theorem we had, betweenness of points theorem. We said that if B is between A and C, then we could add AB plus BC to get AC. That was quite a while ago. What if B wasn't between A and C? What if it was, say, up here a little bit? Would it be a line anymore? No, it wouldn't. And if it's not, would this still be true? If B were up here and we connected them, we would have a triangle, wouldn't we? And maybe you can see why this comes into play here with the triangle inequality theorem. We, however, are going to prove this theorem by using this triangle inequality and an indirect proof. See what happened here? We moved B out. So suppose what? We're trying to prove they have to be collinear, so how are you going to start? Suppose they're not collinear. If A, B, and C are not collinear, connect them to make a triangle. In that triangle, AB plus BC is greater than what? And why is that? So two parts to that one. What contradiction does that pose? So therefore, what we supposed or assumed is false, and what must be true? All right, I like these challenges here. We've got two sides of an isosceles. Don't miss that. Isosceles triangle are 4 and 9. Could you tell the length of the third side? Think about that one and explain. It's not maybe quite as easy as you think. Think it through. Here's another example. We've got a scalene triangle this time. Remember what scalene means. No sides equal. We've got two sides, 5 and 7. What can you tell us about the third side? Anything? Explain why or why not. Now we've got a right triangle, 6 and 8. What could be the length of the third side? Nice little challenges. You may want to sketch a picture. Greek mathematician named Heron, we run into Heron's theorem several chapters later. He's also proving the triangle inequality theorem, that we have a triangle and the sum of two sides, AB plus BC, is greater than AC. Does it in a little bit different way. You follow it through by giving a reason for each step here. So work your way through this. Let BD bisect ABC, so right down here it bisects. They want to know why 1 and 2 would be equal then down here. Now they're suggesting that 3 is greater than angle 2. Encourage you to look at triangle BCD here. 3 greater than 2 and 4 greater than 1. Same reason for both. Now they're saying that rather than 3 being greater than 2, they're saying 3 is greater than 1. Same with 4 and 1, 4 and 2. Why could you do that? And now if 3 is greater than 1, angle 3 greater than 1, they're saying that AB down here is greater than AD down here. Same reason on the other side with angles 4 and 2, sides BC and DC. Next, AB plus BC greater than AD plus DC. I see an AB there, and I see a BC there. I see AD there, and I see DC there. How do you go from step 28 to 29? Next, AD plus DC equals AC. AD plus DC equals AC. Got that reason? And then they close with AB plus BC, AB plus BC greater than AC, which is what we're trying to prove. You see that right up here. But what's the reason for being able to make that final statement? Look at 29 and 30 and see if you can't figure that out. Sticky credit opportunity here for triangle inequality theorem with something beyond a triangle. Here we've got a quadrilateral. And you're trying to prove AB plus BC plus CD has to be greater than that fourth side with a hint. Okay, there it is. Now that light path, we've done this one before, something similar. We know that when the light hits, it creates two angles the same. This particular proof is suggesting that the path from the source to the destination is going to follow the shortest possible route. In other words, from A to X to B. And that is the shortest route possible. So we have a point X. We also have any other point Y. This could be anywhere along here and it would work. So the figure above shows two possible rays of light from a source of point A being reflected by a mirror to a special point X and any other point Y. The light continues to be the destination. They've added some lines here to try to help with this proof. See their marks, CD equal DB. We've got AXC simply telling us that is a straight line. And we've got line M perpendicular to BC. So we got some right angles there, and we got those equal. So we're just looking for reasons here as you work your way through this. See if you can come up with the reasons for each one of these steps. So you just pause it there and see what you can come up with. Finally, they ask which statement above shows that the path of light from A to B to X is indeed the shortest. Which statement shows that the angles of path from A to X to B are equal? So 42 and 43, we're looking for one of these statements up here. Finally, the set 3 work triangle. Geometry is even involved in designing a kitchen. They talk about the work triangle. I guess you use the refrigerator, the stove, and the sink. So this triangle, they figure a lot of people are moving between these three appliances. And they say that perimeter of that triangle should be from 6.5 to 7 meters to be the best design. And that the sink to the stove should be between 1.2 and 1.8 meters. So here's the challenge. Suppose that in this kitchen, the perimeter of the work triangle is 7. So all the way around here is 7. And that the sink to the stove is 1.5 meters. Now they ask a few questions here. What's the sum of the other two sides from there to there? What's that sum? Keeping in mind the total was 7. If X is the length of the refrigerator to the sink, refrigerator to sink, this is X, what would this remaining dimension be? Keep in mind the previous problem. I've drawn the work triangle and put the expressions on there. What would each of these dimensions be? This is X. What's this one? And now you write 3 inequalities. Use that triangle inequality theorem to write 3 inequalities, and then you use those to try to figure out what the length of the refrigerator to sink. What is this X? How long is that going to be? It's a really good challenge, good problem. So give it a try, see what you come up with. Then there's a set 3. You can follow the directions. This is a chart that shows miles between cities. London to Paris, Paris to Rome, Rome to Cairo. Why are these blank? Well, this would be Paris to Paris. That would make no sense. Rome to Cairo is there. Rome to Rome, that wouldn't make sense to have anything there. So these are some distances. Keep that in mind. One of them is wrong. When you go London, Paris, Rome, and Cairo, one of these numbers is wrong somewhere. And they walk you through it here in set 3. See if you can figure out which one of those is wrong and figure out the other dimension.